is Delio Mugnolo from FernUniversität Hagen, and the title, no need to read it, so Delio, the floor is yours.
Thank you so much, Pavel, and thank you all, organizers of this semester program. I've been here for 1 week now, and I'm enjoying it a lot. So it's thanks. It's always great to be in Cambridge and at Untitled in particular. When I was asked to give a talk here, I was wondering a bit what I'm going to talk about, and I decided to present something slightly tangential to the topics that maybe mainstream here in this program, because as you will see, there is a slide parabolic flavor in my talk and in my research I would like to present. So, but maybe there are some nice connections to spectral theory as well. So my story starts in mid-19th century when French physicist Barret de Saint-Venant, he was wondering about the following problem. So assume you have a column or a three-dimensional body, and you would like to twist it. And he was wondering what is the optimal cross-section to oppose such a torque. So is there a given geometric configuration that minimizes the chances that your column should be twisted? And he was deriving a mathematical model for this problem. And in 1856, he came up with this, I don't think this is a very good thing to be doing, using this presenter. So with this elliptic equation, so basically your cross-section is in RD, your column is D plus 1 dimensional. So, and he said that he derived that the stress function for this problem is given by the solution of this elliptic equation from your V with Dirichlet boundary conditions at the outer boundary of your problem, of your geometric object. And overall, the overall capacity to oppose this torque by the column is the torsional rigidity, which is just the L1 norm of this function. Because of a maximum principle, the torsional function will be positive, so actually it's just the integral of this function. Okay, and he was conjecturing that that among all possible bodies of given area for the cross-section, or say volume, in higher dimension, then the ball will be optimal. But this couldn't be proved by the techniques that were available back then. This was proved by Poglia in the 40s. The proof is very easy once you have the right tools. Basically, so first of all, he could set up a variational framework for this problem. So he showed that the torsional rigidity is nothing but the supremum of this quotient, which you can, because the function is positive, you can also write in this way. And now you see it's very similar to a Rayleigh quotient. The main difference being that you have an L1 norm instead of an L2 norm there. But the other things are, I mean, the crucial aspects remain. So it's still a homogeneous quotient. So you can apply symmetrization. And basically, very much like you prove the Faber-Kran inequality, to show that the ball minimizes the ground state energy of the Dirichlet Laplacian, you can also show by the very same tools essentially that the ball maximizes the torsional rigidity. Okay, that's a nice story. So as I was just mentioning, so the ball minimizes the ground state energy and maximizes torsional rigidity. So it's a natural question to wonder, assume you are multiplying them in a nice way because they do not scale in the same way. So torsional rigidity is measured in cubic meters or feet because we're in England, and eigenvalues are 1 over square meters. So you have to make this product scale invariant. But once you renormalize this product, which term is winning? So is like is the ball a minimizer or a maximizer? Maybe neither. And he conjectured that actually it is a minimizer for the product. But this problem proved very hard to attack. So it was an open problem for many decades, for several decades, until in the late 1970s, Collot-Jobin, she proved it. So she proved it in all dimensions. And, and then there is this nice paper by Brasco some 10 or 13 years ago that presented as maybe a slicker way of proving or performing Collot-Jobin's proof with lower regularity, which was a crucial aspect in something I will tell you later. He also proved it for the P Laplace and for different stranger, more exotic objects. But so basically, this is a nice, difficult variational, so inequality can be proved by variational methods. And basically, until a couple of years ago, Laplacians or P Laplacians on domains were the only known environment known where a Collot-Jobin inequality holds. Okay, so for instance, just to mention one, so for instance, it's not known if there is any reasonable way of formulating this conjecture, or this inequality for the Robin Laplacian. Okay.
Is the equivalent inequality for the torsion for Robin Laplacian known, or is?
Yeah, I mean you can prove it. It's certainly proven for the main topic of my talk, which are metric graphs, which I'll introduce in a second. I am not quite sure about domains, but I'm pretty sure that the proof carries over. So, but I actually think so. Yeah. At least if the Robin coefficient is the right sign. Okay. So let me present a couple of examples just as a sanity check. So easiest possible case, interval. Interval of length L with 2 Dirichlet boundary conditions. You can write down the torsion function explicitly. This is simply this object here. So it's it's a concave function, as you would expect by the fact that its second derivative is negative. And it's convex. And the torsional rigidity can be computed explicitly, which is just this number here. So for the Collot-Jobin product, what you end up is a precise number like that. So everything is explicit. So this is the nice thing about, of course, about one-dimensional problems, is that they can be, in many cases, you can have an explicit formula which you don't have for general domains. And in fact, this is something I will be developing or elaborating on in the remainder of the talk, because an interval is nothing but a metric graph. I mean, metric graph can be very complicated, but an interval is a special case of a metric graph. And just in case you were wondering, so for metric graphs, there are a lot of heuristic arguments now available in the last 30 years that suggest that intervals in the realm of metric graphs, intervals are the correct counterpart of balls. So whenever you have a spectral geometric inequality involving a ball for domains, then usually something similar will hold for metric graphs having intervals as optimizer. Okay, what is a metric graph in case you haven't stumbled upon them in the past? So what you have is basically, what you do is you start with a graph, those you learn in combinatorics or discrete mathematics, but you associate or identify each edge of this graph with an interval. So a graph in a combinatorial sense is simply a set of vertices that may or may not be joined or be adjacent, mutually adjacent, but this is a purely abstract relation. So there is no physical or geometric interpretation of this adjacency. In a metric graph, so you turn this abstract relation into something very tangible. So you say 2 points are connected by a line. And because on a line you can define functions, you can also define operators, which is exactly what I'm going to do. So more at more abstract and maybe sometimes more useful level, what you do is the following. You consider a family of intervals, and each interval carries a certain metric and a certain measure. So if you glue them all together, then you end up with a natural sum measure. And you also end up with a metric, and the metric is simply given by a quotient structure. So basically, you're taking a metric graph is this joint union of intervals after you take a quotient with respect to a certain equivalence relation. The equivalence relation means how you are gluing vertices in a certain way. So this means that basically once you have a certain number of intervals, you can associate with these intervals a lot of different graphs after gluing the intervals in different ways. So you can wonder whether with respect to certain functional, say, eigenvalues or maybe torsional rigidity or whatever, certain configurations are more appropriate or optimal than others. Okay, so long story short, after this abstract construction in terms of quotient, metric, measure spaces, you end up with a metric measure space structure on a metric graph. And in this way, you can also define a natural way spaces of continuous functions, Lebesgue spaces. And crucially, you can also define Sobolev space on a metric graph. So Sobolev space can be constructed in a way intrinsically once you have this abstract construction, just by saying you take all functions that are continuous over your graph. This is interesting because otherwise you would lose the topological information given to you by the graph. So it would be, you wouldn't mirror what actually the graph looks like. And functions that are square integrable. Okay, that's natural in context of spectral theory. And whose weak derivative is also L2. Fine. So this is a Sobolev space. And to our purposes, we will always assume that we have some Dirichlet conditions at some vertices. So this is why we have this VD set, so this Dirichlet vertex set. Okay, so this is all we need to start playing, because then we have a Sobolev quasi-norm. And this quasi-norm is actually a closed quadratic form in L2. So we can associate a nice self-adjoint operator in L2 with this form, which we call the Laplacian on a metric graph with.
If you take vertices that are not in VD, do you have something like Kirchhoff conditions?
Right. So very good question. So the point is that once you have the continuity condition in those vertices, so the function is continuous everywhere, so in particular in these vertices you are mentioning, and by imposing that the associated operator self-adjoint, by integrating by part, you automatically get this Kirchhoff conditions. So you have, this is exactly what I wrote here. So basically the domain of this operator consists of edgewise H2 functions with exactly the conditions you were mentioning. And because in my talk I will always assume that the graph is compact, so finitely many edges, each of them of finite length. This setting can be largely generalized, and it's actually a very interesting topic, but I'm not mentioning it right now. You have easily a compact embedding of your form domain into L2. So in particular, I have compact resolvent, pure point spectrum, countably many eigenvalues accumulated at infinity, each of them real and non-negative. You can see that lambda 1 is 0 if and only if the graph, if and only if you have no Dirichlet vertices. But otherwise, we'll always have a strictly positive ground state. And there are some nice properties coming from maximum principles. So you can show that, well, basically you know that you can show that the inverse of the Laplacian is a positive operator as soon as, so because of what I just said, the operator is invertible if you have Dirichlet vertices. And in this case, then you always have that the inverse is a positive operator. And in fact, if we assume that the graph minus the Dirichlet set is connected, then it's even an irreducible operator, so a positive improving operator. So from now on, we will always assume that there are Dirichlet vertices. Otherwise, a lot of things I would be saying are trivial. OK, so what is torsional theory and a metric graph? So basically, the starting point is exactly the same. So you take the same elliptic equation, a metric graph with Dirichlet condition on certain vertices. That's fine. Again, the torsional rigidity is simply either the L1 norm of the solution, or by the same argument introduced by Poglia, the maximum of this quotient, which I like to call the Poglia quotient. And in fact, this is not a very new topic. So torsional rigidity issues on metric graphs have been studied for the last 10 years by several people for different purposes. What I was interested in when I started working on this topic some 5 or 6 years ago was to basically replicate or see if these results by Poglia and co. Can be carried out. Well, can be carried out in the setting of metric graphs too. And it turns out that quite a few things can be extended to metric graphs. So in particular, you have this kind of Saint-Venant inequality. So let me remind you, Saint-Venant conjecture that the ball is the optimizer, so it's the maximizer for the torsional rigidity among all possible configurations of same volume. And for metric graphs, this holds. If you so you have this estimate here. This is the total length of your graph, and this estimate is sharp in the sense that you can have an equality, and the equality holds if and only if the graph is a path. So it's an interval. Nice. There is another nice thing you can do using symmetrization. You can count the cardinality of your super level sets when you try to symmetrize your function. And by doing this in an appropriate way, which I borrowed from some nice paper by Rami Band and Guillaume Lévy, who did some similar things for eigenvalues, then you can actually improve this inequality in the case of a if you know that your graph is doubly connected. So if you know that you have to cut at least 2 edges in order to disconnect your graph. This is a sharp estimate, and this is a counterpart in the case of domains. So I didn't write it, but 2 years after Poglia proved that, so his inequality is proof of this Saint-Venant conjecture, Poglia and Weinstein, they publish a paper in Annals showing an improved inequality in case of not simply connected domains. So again, they proved that an annulus is the optimal configuration for the torsional rigidity. So basically, this is this kind of version of this Polya-Weinstein inequality for metric graphs. Okay, this was not very difficult to prove. So again, it's symmetrization, just like in the case of domains. So we were challenged to, we is Marvin Plumer, my earlier doctoral student, and myself. Oh, sorry, here it should be 23. If the Kolozov-Bonn inequality holds. So we could prove it. But this is much more difficult proof. So the whole point why Kolozov-Bonn inequality was open for so many years is that usual symmetrization techniques do not work. So if you try to read Kolozov-Bonn's paper, it's instructive, but it's a complicated proof. So it goes in different steps. You have to solve a certain non-trivial ODE and show that for the solutions of the ODE you can apply certain symmetrization techniques. So it's a very interesting approach. And something similar had to be done for metric graphs. And this is difficult because in Kolozov-Bonn's argument, it was crucial that the solution of certain problems are C-infinity. And on a graph, things are never C-infinity because of the things you were asking before. So if you have Kirchhoff condition, this breaks down the possibility that the function is infinity. You will have a discontinuous first derivative of any relevant function, in particular eigenfunctions. So we had to use the relaxed version by Brasco of Kolozov-Bonn's argument, which only requires Lipschitz continuity of a solution of certain things. And luckily, you can show that eigenfunctions on a metric graphs are Lipschitz continuous. So everything is fine. So we could carry out the relevant arguments. So we could prove that the interval is a minimizer among all possible graphs of given total length. The interval is the minimizer of this product, just like you would expect from Kolozov-Bonn's argument. So this is exactly the number we saw before when we were working on just on one interval. And because the proof goes through symmetrization, as I said, we can again apply similar ideas for, as I showed in the previous slide. So counting the sublevel sets of a certain symmetrized function, you can actually prove an improved Kolozov-Bonn inequality for doubly connected metric graph. And this is something I find nice and slightly puzzling because, as far as I know, Kolozov-Bonn inequality for non-simply connected domains is not available on domains. So it's totally open if something like that could be true on domains. There are reasons why it's even less trivial on domains than on graphs, but we can discuss it later if you wish. Okay. Okay. So this is basically the starting point of what I really wanted to tell you. So this was part of a project of a doctoral thesis of Marvin Plumer. But then I was wondering what one can say about a different kind of problems on metric graphs, namely about heat equations. So my background is actually semigroup theory, so I worked a lot on Dirichlet forms on metric graphs. So actually, I was always interested in heat semigroups and Dirichlet forms on the structures. And the question is, so we have nowadays a lot of results telling you which configurations are optimal with respect to eigenvalues, now torsional rigidity. So certain variational quantities. Can you say anything about optimal configurations for the heat equation? And this is the main topic of the rest of my talk. And the answer is, as usual in life, well, it depends. So what I would like to start with is just to give you a brief reminder of the theory of heat kernels, in case you are not familiar with them. So heat kernel is defined as the fundamental solution of the heat equation. So basically, you take a certain domain of your favorite kind of geometric domains, you apply as initial datum a delta, a Dirac delta at a point, and try to solve the heat equation with this initial datum, and what you get is the heat kernel. And the heat kernel has a nice property that, because of linearity of the heat equation, that you can also represent the so the heat kernel is this Ptxi axy, and the nice property is that once you have an initial datum f, which is not a Dirac delta, you can now represent the action of the semigroup on the initial datum f in this way, as an integral of Ptxy against fy. So if you are on on Rd, then it is simply the convolution of the Gaussian kernel with the initial datum. In general, it will be something which is not a convolutionary type, but it's nice to know that you have a function like that. So you have to prove that you have a heat kernel, but in most cases you do, not only for the heat equation, also for the more complicated operators. So a priori, a heat kernel is simply a measurable function that has certain properties. In particular, it is L2 in each coordinate. And then this guy, of course, needs to be integrable for each f in L2. And then there are actually quite a few interesting results telling you that this heat kernel, in many cases, is much more regular than merely L2 in each coordinate. So you can have, in some cases, it is continuous up to the boundary on domains. And in fact, you can show that the fact that it is continuous up to the boundary is equivalent to certain capacitary or potential theoretical properties of your domain. This is something that Wolfgang Arendt did in the 90s, very nice. You can show in certain cases that you have even higher regularity, that in certain cases you have even Hölder continuity, which is interesting because a few proofs available for, a few available proofs for showing Gaussian estimates of heat kernels are based exactly on the fact that you have Hölder continuity. So I was wondering if there is some structural way to prove Hölder continuity or even Lipschitz continuity of heat kernels. And it turned out that it is possible. So there is this nice result I just got with my doctoral student, Patrizio Bifulco. So assume that you have an operator A that generates a semigroup, and you have an associated heat kernel. Assume that there is a K, no matter how large, such that the domain of the kth power of A, as well as the domain of the kth power of the adjoint of A, both embed in some Hölder space. Then, for some exponent alpha, then you can show that the heat kernel is actually jointly Hölder continuous. And in fact, even more, you can show that, okay, you would like to have something like C1 alpha, but this is not possible. So as I told you, reasonable functions, so functions in the domain of the Laplacian will not be C1 on a metric graph, for instance. So in general, you cannot expect anything like that. But if you're in an abstract metric measure space, what you can do is you can hope that this operator A applied to the heat kernel is still nice enough. So this is a proxy for higher order regularity in this very general metric measure space setting. So this is what I have. Sorry, this is a typo. This should be a star. So what I mean by that is that if you apply the operator A to the first coordinate of the heat kernel and the adjoint of A to the second coordinate, then this will still be a C0 alpha function. So it's actually more than I was aware of in the case of domains. And this is even for very general metric measure spaces. And yes, as I was saying, so this is in general optimal in the sense that if you take in particular metric graphs, which is a special case of this, then you cannot get C1 alpha property. So this is the best you can do. So specialized to the case of metric graphs, what you have is that, in fact, the semigroup generated by the Laplacian I was showing before has a heat kernel. The heat kernel is positive, is a positive function by some, well, basically because you have a, because the quadratic form I was showing before is a Dirichlet form, so the semigroup associated with this form satisfies a parabolic maximum principle, so the heat kernel must be positive. And by the previous theorem, you can also show that it's Lipschitz continuous, jointly Lipschitz continuous in both variables. And well, if you are in a non-Dirichlet vertex, then this term here will even be strictly positive. So from now on, I'm using this notation here, so please remember it because we'll see many times. So PTGVD is the heat kernel at time t for the graph G with a certain Dirichlet set. So I will sometimes compare different graphs with same Dirichlet set or different Dirichlet sets and so on. So let me stress that there is a connection with what I was presenting in the first half of my talk, because if you integrate your heat kernel in both space variables and in time, what you get is, by definition, the oh, sorry, this is sorry, there should be another integral in G here. So this is just integral of the semigroup generated by the Laplacian applied to the constant 1 function, integrated in space and time. And because the resolvent of a generator is simply the Laplace transform of the semigroup, this is simply the integral in space of the inverse of the Laplacian applied to 1. So basically the integral of the double integral of the green function, and this is precisely by definition the torsional rigidity of your graph. So understanding the heat kernel on a metric graph gives you an insight about the torsional rigidity. In a certain sense, it's also a finer insight in the sense that the torsional rigidity is all inequalities for the torsional rigidity are integrated versions of inequalities for the heat kernel. So ideally, you would be able to show nice inequalities for the heat kernel. This would give you something for the torsional rigidity. Sometimes it's possible, sometimes not. So what I presented you before are results that for which I couldn't find a proof using the heat kernel. But certain things can be done, and this is the main message today. So in a certain sense, the torsional rigidity can be seen as a thermal insulation of your body. So this means that once you apply Dirichlet conditions, so if there are no Dirichlet conditions, then the heat is conserved, is kept into your system. It's just like a body with a domain with pure Neumann boundary conditions. But as soon as you apply a Dirichlet condition somewhere, it's like like applying a nice bath at in a certain region. So heat will start flowing out of your body, and depending on how large this Dirichlet set is and where it is situated, then you will have different ways of losing heat at each time, and also integrated in time. So this is exactly what is described by the torsional rigidity. So torsional rigidity is the overall decay of heat of your system, in a sense. So okay, and maybe just let me comment. So basically, this means that if you have a graph and you want to you must apply a Dirichlet condition somewhere, but you would like to keep the heat as long as possible in time overall. in your metric graph, then the best way of doing so, of applying a Dirichlet vertex, is to take simply an interval and applying the Dirichlet point at one endpoint of your interval. Okay. Again, what you could do is, again, in an interval, I think it is instructive. So consider again an interval of length L. And then now we are playing a bit and we are applying a Dirichlet point S somewhere in the interval. So I just said, so if I apply S at one endpoint, then it's guaranteed that I have optimal insulation. And then if I start moving it towards the center, then the insulation will get worse and worse, and you can measure it. So you can actually compute the torsional rigidity of this system. I mean, it's a bit trivial in the sense that they are simply two disconnected intervals whose total length, so combined, is L. But still, you can do it. And then you will see, I mean, it's not maybe a surprise, that the minimum of this function is, as you can guess, exactly in the middle. So if you put Dirichlet conditions in the middle of this interval, then you will have minimal insulation. Now, the question is, can you do the same for general graphs? And yes, you do. I mean, you can. So the torsional rigidity, so now assume that you have simply one point where you can apply Dirichlet conditions. What is the optimal way of applying it? I mean, to decide where to put Dirichlet conditions. And so at every time you apply condition at one point S, you will have a new torsional function, which I call Vs. And associated with this Vs, there will be an integral, which is the torsional rigidity for this graph with this problem, with these prescribed Dirichlet conditions. Now, if you differentiate this function as a function on, so S is now, let me stress, S is a point on your graph. So if you differentiate it with respect to S, then you apply Leibniz and you get this guy here. And very little is known about this function. So as I said, on interval, a maximum is at both endpoints, and the minimum is in the middle of the interval. The same holds for a star graph, so something like that. So if the three edges have the same length, then the minimum of that function here will be here in the center of the star, and the maximum is in all three endpoints. But for general graphs, this is open. So I think it's an interesting geometric question, because in a certain sense, the minima of this function can be understood as the centers of a graph, and there are not so many notion of center and convexity for metric graphs. So I think that this might be a nice possible approach to this question. Okay, now I'm slowly going to conclude. So the final object I would like to introduce is the heat content. The heat content is a relaxed version of the torsional rigidity, if you wish. So this is a notion or an object that was introduced by Michel van der Berg and Brian Davis in the 80s. So what they did is the following: assume that you have an operator that is known to have a heat kernel, say the Laplacian on a domain with Dirichlet boundary conditions. You just integrate the heat kernel in both space variables, but keep the dependence on time, this quantity here. And the nice thing is that you have basically by Mercer's theorem, you can Fourier decompose the heat kernel, and you have this equivalent description in this way. So you have a sum over all exponential of eigenvalues multiplied by the integral, not the L1 norm, the integral of each eigenfunction Vk squared. And it's interesting. So let me please appreciate that this description have very different flavors. For instance, if you want to prove that the heat content is a positive function, it is absolutely trivial starting from this description here, because the heat semigroup is a positive operator, so the heat kernel is also a positive function. So if you integrate a positive function, of course, this guy is positive at each time. But I think it's an interesting challenge to prove positivity of this guy here by using this expression here. So sorry, yeah, sorry, I was not correct. In what I was meaning is that if you, okay, sorry, you're totally right. What I meant is proving that the heat kernel, based on the Fourier expression, is a positive function. So Ptxy is e to the minus t lambda k vk x vk y. And that this guy is positive is totally unclear. I mean, you can, if you by your favorite computer algebra system, you can prove it. But I mean, you can observe it, but it's not easy to prove. But okay, you're right. Of course, this guy here is now positive. You can show easily that there is an estimate between the heat content and the trace, which is something more maybe more familiar or more usual to study. You can even write it down explicitly in the case of an interval with 1 or 2 Dirichlet vertices. And now something interesting happens, or you can observe something interesting. So this is for an interval with mixed boundary condition, or with pure Dirichlet boundary condition, we have this expression here. Now, oh, sorry. Sorry, this L here is the same L as here. So what you see is that the leading, so there is this factor here. So as t goes to 0, this term here goes to 1, and then you see the total length, so the length of your interval. So you can, the asymptotics of the heat content on an interval maps, so gives you, for short time, gives you the length of your interval. This is nice. But if you nicely factor out this guy here, so basically if you renormalize your heat content, and then you plot this object here, this series, you get something interesting. You see that this guy here, so you see here you have the number of Dirichlet points. And you see that you get, in the short time asymptotics, you get -1 if you have mixed boundary conditions, and 2 or -2 if you have pure Dirichlet boundary conditions. So this suggests that the short time asymptotics of the heat content also tells you something about the size of the boundary of your domain. And this is something that indeed Van den Berg and Davis could prove in the 80s. And in fact, there is a nice follow-up paper by Van den Berg and Gilkey where they prove that, in fact, I think for manifolds even, and then there are many later papers extending this more and more. Well, what Van den Berg and Gilkey proved is that on a domain with Dirichlet boundary conditions, the short time asymptotics of heat content has a full expansion in powers of t to the power n halves. So beta 0 is the volume of your domain. Beta 1 is your perimeter. Beta 2 is beta 3, beta 4, and so on are different notions of a curvature. And you have infinitely many terms. So I think, as far as I can remember, the first 20 or so have been computed explicitly, but you know that there exist such things. You can, yeah. No, what sorry, maybe it was sloppy. So what I mean is that you have, so this is 0, L, and other you have Dirichlet, and Dirichlet or Dirichlet and Neumann. So just at the endpoints. So you can guess what I would like to do is now to see if the theory of heat content has a nice counterpart also for metric graphs, and it does. So in a graph with a certain Dirichlet set, then you you just define the heat content in this way, and again you have a description in terms of the eigenfunction. That's fine. And now, what's the main difference between domains and metric graphs? Now, on metric graphs, you have a crucial tool that is not available for domains. There is a very nice formula proved by Roth in the 80s, which is the heat kernel. So for a metric graph, you can write down explicitly what the heat kernel is, which is something, it's almost magic. So there are, I mean, you can do it, of course, for RD, you can do it for hyperbolic spaces, and there are, I would say, very, very few cases, maybe both with objects with certain symmetry. But in general, of course, you cannot say anything about the heat kernel. But for metric graphs, you have the semi-explicit formula. But let me make this more explicit. So maybe let me comment on it. So what's here is the following. You have, so it's an infinite sum. So what you do is the following. You take 2 points x and y in your graph. You take, so for instance, say, this point and this point. Now you take a path from x to y. Okay, let's call it P. And this has a certain length, and you can plug this length in the Gaussian kernel, one-dimensional Gaussian kernel. And this is nice. This you can do. This gives you the leading term of your heat kernel. But the problem is that you will have to do it infinitely many times, because there is not only one way to go from x to y. You can also go from x to y like this. You can also go from x to y like this, and so on. There are infinitely many crazy possibilities of going from x to y. You can bounce between here and here 10,000 million times and then go there. And each of these terms will give you a contribution to this series. So you can imagine that this series will easily get out of control, and it does. The good thing is that you have this nice factors. Oops. Alpha here, which I will not write down explicitly, but they are so-called scattering. So they are products of so-called scattering matrices, and they tell you how unlikely a certain path is to be optimal, so to say. So this is very, very heuristically explained. So if you bounce back and forth 10,000 million times and then go back here to y, this contribution will be weighted by an alpha, which is very, very small. So it basically will give virtually no contribution. So the interesting thing is that the series does converge. And it gives you a precise expression at all times at each t. OK, so when I started working on eigenvalues on metric graphs, it turned out, so one of the people I worked on that with was Grigori Berkolai, who was here until last days, and James Kennedy and Pavel Kurasov. What we did, we quickly realized that surgery tools are very crucial things, crucial tools for spectral theory metric graphs. So essentially, the possibility of modifying the configuration of your graph in order to change eigenvalues in a controlled way is very important. This is something that is much harder to do on domains. You can symmetrize, and this is pretty much it. But it's very difficult to take a piece of a region of a domain and move it to another point. But this is something that you can often do in a nice way on metric graphs. So we were trying to replicate similar ideas for the heat content, and this turns out to be much more difficult. So certain things can be done in an easy way. So for instance, if you increase the size of the Dirichlet set, things are fine. So you reduce your heat content if you have a monotonicity with respect to subgraphs. But even if you try to do something similar like rescaling, this property is obvious for RD because of the Lie symmetry groups of the heat equation, but doing it for the heat equation on a metric graph already requires this strange formula I just showed for the heat kernel. And then you have more complicated things. For instance, you can prove that if you lengthen an edge that is incident in a Dirichlet vertex, then you have a certain behavior. So the heat content goes up. But it is important that you actually are really lengthening an edge adjacent to an incident in a Dirichlet vertex. If you can show that you can, if your graph contains a loop and you cut in the middle of your loop, then the new graph has exactly the same heat content. You can prove some mirroring symmetries and so on. So these three objects are a pale counterpart of the zoo of results you can show for eigenvalues on metric graphs, and they are much, much more difficult to prove. And the main reason is that you don't have a nice variational approach to the heat content or to heat kernels as you have for the eigenvalues, and even for the torsional rigidity. So this is maybe the paradox of this theory, that the torsional rigidity is the integrated heat content in time, but because the torsional rigidity has a variational structure which the heat content does not have, it's much, much more difficult to prove things for the heat content. Okay, this is basically almost the end of my talk. This is the main result we could prove in a paper that just got accepted a couple of days ago in Henri Poincaré. So we showed a formula for the heat content, and unlike the one proved by Van der Berg and Davis, this holds at all time. So we can prove that there is a leading order term, which is just the volume of your metric graph, so the total length of a metric graph, a second order term that contains the size of a Dirichlet vertex, and then this term here that contains, this is in a certain similar to this formula by Roth, but instead of the exponential here we have this function h, which is defined like this. It's a strange function, but it's very nice in the sense that it decays very quickly, even quicker than the exponential. And that the paths you have to consider are all paths that start at the Dirichlet vertex and end at the Dirichlet vertex. So it's the proof of this theorem starts working with Roth's formula for the heat kernel, and then it's very, very complicated bookkeeping of all contributions given by this paths starting and ending at the Dirichlet vertex. So I think I will not show you the proof, which is very technical, but let me just mention that in particular, if you do the small time asymptotics of this formula, you can trivially see that there is an expansion like that, just like Van der Berg and Gierke proved. But in this case, in case of metric graphs, it is trivial in the sense that for all n larger than 2, it's identically 0 because you have this sub-exponential term here. So it's a very interesting property, and it is different, for instance, from what is known for RCDKN spaces. So RCDKN spaces are metric special spaces of a certain dimension and curvature, and crucially, it was proved, so it's a byproduct of a result which is like 2 years old, that metric graphs are not metric measure spaces. Are metric measure spaces that are not RCDKN spaces for any k and n. So it's this result by Caputo and Ross is it's a counterpart, but it's not directly comparable with what we have. Okay, I will not show the proof, which is technical and ugly, but difficult. Let me just make very quick, actually 2 advertisements. The first one is for a beautiful result obtained by Matthias Stoifer, also with Patrizio Bifulco. So they prove a kind of Faber-Kran inequality for for the heat content. So what they do is the following. They show that if you have a graph G, then there is a time t, 0, such that for all larger times, the heat content of an interval will be larger than the heat content of your given graph. And T0 does depend on the graph. And likewise, that if you give me a graph G, then I will give you another time T naught prime, such that for all times smaller than that, then the path will maximize the heat content. And the funny thing is that the proofs are totally different for large times and small times. One uses torsional rigidity methods, the other one uses Brownian motions. And it's absolutely open what happens in between. So the natural conjecture would be that the path is always optimal for the heat content, always maximizing the heat content, but it's not known. So if you are interested in this topic, then you can try it. And would have interesting applications, if, for instance, if you want to do some kind of parameterized clustering or partitioning of metric graphs. This would be a very natural and nice approach, but it would need the intermediate times. Yeah, I think I will skip this one. Maybe let's just mention that we can also prove in a nice way this Cacciopoli type inequality. So there's a very nice approach that goes back to the Georgian Cacciopoli, how to measure perimeters of very ugly domains, very rough domains, through the heat semigroup. So basically what you measure, so the intuition is that the heat going out of your ugly domain gives you information on the size of your boundary, and the same can be done also for, of course, with very different proofs also for metric graphs. The last thing I want to mention is my second commercial. So there is something that some of you already are aware of. So I am the speaker of a cost action. So cost is basically the small sister of the ERC. So it's a European Cooperation in Science Technology. So it has a certain number of formats, but the actions are the main one. So there are networks of people from different European countries that start working together. So ours is called MSpace, and it started in November. At the beginning, we were 40 applicants for 20 European countries. And the reason why I'm mentioning it now here is that unlike most formats you're aware of, cost actions can also grow in time. So actually, we can, and this is expected from us, that we attract new members over time. And in fact, after 6 months, we already have 280 members from almost 40 countries. There are 4 working groups. The first one is on, say, discrete analysis, and is led by Pavel Kurasov. The second one is on spectral geometry, and one of the leaders is actually Asma. The third one is on gradient flows and optimal transport, and the fourth one is on stochastic geometry and application to material sciences. So I think there's a large spectrum of topics. So in case you're interested, then please reach out. And with that, thank you for your attention.
Always, thank you, Delio. So questions? Yep.
And you go back to slide 11, please. So yeah, in the second case, do you reckon that we have something like if G has Betty number, so in terms of the first Betty number, then this inequality should be pi over cube root 12 times Betty number plus 1 with equality if and only if it's the necklace with exactly that correct number of things. Is that actually what you prove, or you just look at doubly connected and that's it?
Good question. The point is that, so what I prove is that I was saying, so if you symmetrize a function, then you see how large the the size of a sublevel set is, and then you see that for a doubly connected graph, then you have at least cardinality 2 in this sublevel set, and this is how you can prove it. And we were, so, okay, this is part of the history was mentioned before. So Barnard and Levy came up with the proof for the doubly connected case. And at the same time, so in the same days, actually, same weeks, Grisha Berkolaiko, Pavel Kurasov, James Kennedy, and I were actually trying to prove the same for general Betti number. And it was quite surprising for us to see that it doesn't work. So if you have a triply connected graph, and the reason is simple. So I think the easiest way of seeing it is that if you have something like this which is triply connected, then you can have something which we called an ear like that. And this ear is, for all purposes, is the irrelevant thing. So this is a perturbation of the ear. So basically, this is the guy that will dominate. So what we had is, so if you check this paper, it is JFIS A 2017 with Berkolaiko and co, is that we have an estimate for lambda 1 in terms of the Betti number, but is less nice than the one for the purely doubly connected case. So this is now for lambda 1. I have no idea what the torsional rigidity does for highly connected graphs, but I think that the same phenomenon will appear.
More questions?
I have a very simple question. I'm confused about something. So the second inequality for a smaller class of graphs, right?
Yes.
But then the lower bound is smaller.
It can very well be that I've mixed them up. So sorry, it could. I will have to check it, but yeah, I think this is what happened. Sorry. So the improved equality estimate should be, of course, the second one. Thank you. This is embarrassing.
Okay, more? If not, well, let's say. Okay.